All right. So good morning, everyone. Welcome to our last class for the fall term. And here we finally have reached our real goal, which is to try to understand some of the Ptolemaic system, the culmination of Greek astronomy. All of the devices that we've seen so far, the different epicycle, the eccentric point, the idea of the Earth at the center, the geocentric system itself. This all culminates finally in the work of Ptolemy. Ptolemy actually is beyond the BC. Ptolemy's dates are more like 100 AD. We're very much in the Roman Empire. Worked in Alexandria his whole life. A Roman citizen, has a Roman name, but was a Greek spoke Greek, taught Greek, was still the Greek center of the intellectual world, the Roman world, but he was a Roman citizen of Alexandria, and we'll talk a little bit about his life and his other accomplishments as we go on. So the Ptolemaic system, as you can imagine, guys, is enormous and enormously complicated, not only just mathematically, but before we even get to the mathematics of it, it's what it's describing. It's just trying to describe the sky as we see it. It's trying to be, in some sense, a stellarium, a planetarium program. Not quite as what we'll see at the end, where it differs from a planetarium program. But what it's trying to describe is so many details, so much information. It's trying to tell you, it's trying to compute for you what the sky would look like, and any object in the sky any time in the past, in the present, in the future. It's a tremendous undertaking to have a system like this at this level of detail. We, of course, can't talk about that level of detail in any kind of meaningful way. This would be a life's work to study the Ptolemaic system at that level, which is exactly what the astronomers after Ptolemy did, right up through Copernicus and beyond, is to first of all master this incredible system. What we're going to do is we're just going to take a few of the key constraints of what the sky watchers tell us must be so for any such application, any such description of the sky. What do you have to get right on some of its most fundamental levels? And these we've talked about. We've talked about some of these, and we're going to introduce a couple more this morning, and then see how Ptolemy's system accomplishes these constraints. The first one we're very familiar with, we've been talking about for a long time now, the retrograde motion of the planets. This really would be the centerpiece, the central problem of astronomy, is how do you describe these very strange loop paths in the sky of the planets? Okay? The stars move in the simplest of ways. They simply rise in the east, move in the west, depending on how big the circle is, or they just simply circle around the North Star continuously in a continuous motion, the simplest kind of motion you can think of. The sun and the moon continue to, of course, rise in the east and set in the west like everybody else, but their motion night to night, their motion through the year for the sun and the month for the moon is to move east through the sky in a steady way. The moon and the sun never move backward. They never have a retrograde motion. They have no loops against the celestial sphere. The planets are different. That's why the derived word is the Greek from being the wanderers. They have a much more complex motion. And this was the great problem, great mathematical problem to solve. How can you build a system which can accommodate this kind of complex motion? And there are 5 planets like this who do this. The Greeks thought of the moon and the sun as planets, but there are 5 wandering planets, and their motions are quite independent of each other. They have certain characteristics the same, but they're also kind of off on their own agenda as well. How do you accommodate this? How does particularly Ptolemy accommodate this? So this is what we're going to do: is we're going to pick out some of the very, very key features, describe them, think about them for a minute, and see if Ptolemy can build a geometric model to accomplish that. And the first one would be the retrograde motion of the wandering planets. Another interesting thing about the motion of planets is, in addition to the moon, is they all move very close to the ecliptic. Remember, the ecliptic is the path that the sun makes through the celestial sphere against the constellations of the zodiac. And the planets are not moving all over the place. You'll never see, for example, any planets near the North Star. Never. The North Star is not near the ecliptic. All of the planets and the moon also come very tightly to the ecliptic, sometimes a little bit above it, sometimes a little bit below it. They move from above to below, but it's kind of like a yellow brick road. The ecliptic path of the sun against the celestial sphere is kind of like a yellow brick road that all of the planets move along. And this picture here, down the lower right, is I'm trying to depict that for you, to remind you of that. Here is a nice picture of all the planets. It's a conjunction of all the planets on a June morning of this year. And you can see there's the blue line is the ecliptic, which is where the suns will move through the year. And sure enough, all of the planets are very much hovering around that ecliptic, sometimes below, sometimes above. So here's a property that the sky watchers have been reporting for centuries, thousands of years. And why is that? Why do all of the planets and the moon continue to move very close to this path that the sun makes in the sky each year against the constellations of the zodiac? So we'd like to see if Ptolemy's system can explain that. And here's just another picture of that idea that this is a time-lapse picture of many of the planets as they trace their path in the sky, and you can see the retrograde loops of the planets, and you can see they're all in this kind of this yellow brick road, this path, this very wide path, in which the middle of it is the ecliptic, the actual path that the sun carves through the sky year after year. So here's a constraint, and a fundamental one that the system certainly should be able to accommodate for us. We know, going back to the retrograde, that we find that the wandering planets, and I'll use the word planet in the modern sense here this morning, as opposed to the sun and the moon, that when the planets do go into retrograde, they are at their brightest. This is a characteristic of all 5 of them. And everyone recognized that brightness means closeness. These are lights, after all, in the sky. And so one of the great constraints that Ptolemy is going to have to come up with is that when you're in retrograde, you should be brightest, you should be closest to the Earth. If you're not, your model cannot be right. So here's a very important constraint that we will watch, that you get retrograde motion, the planets are at their brightest, and therefore they are at their closest to the Earth. Of course, everything is going around the Earth in Ptolemy's system. So planets are brightest during retrograde, and therefore they're closest during retrograde. And here's the third idea that I want us to think about, and you take this as another very important constraint. This is the idea of the elongation of a planet with the sun. You can actually have the elongation of anything with the sun. The elongation of any object in the sky is simply the angular separation that we see from that object to the sun. For us, most importantly this morning, we're talking about the planets. So when you look at Venus on any given night, and you can see where the sun just set, where the sun would still be below the horizon, you can ask the question, what is the angular distance from Venus to the sun? How far is that? The 2 most important elongations are 0 and 180. The elongation of 0 is like the new moon. That is, there's no separation between the sun and the planet. The moon is right in front of the sun. And that's why we have the dark moon, the new moon. An elongation of 180 degrees is when the planet is on the other side of the sky. It's on the other side of the celestial sphere. The angular separation is the full straight line of 180 degrees. And that's just like the full moon. And that's what we saw on Monday night, Tuesday morning, with the beautiful eclipse. I don't know if anybody caught some of that towards the early morning to see a bit of the red sun, a bit of the red moon in the shadow of the Earth. But the only time you'll get a lunar eclipse is when you have a full moon. When the sun is on one side of us, the moon is on the other side of us, and so therefore the moon can move into the shadow of the Earth. That's an elongation of 180 degrees. Okay? So those two elongations are the two extremes. The elongation of 0, like the new moon, that's called a conjunction. And an elongation of 180 degrees, in which you're on the opposite side of the sky from the sun, that's called, not surprisingly, an opposition. And there are certain constraints that the planets have in terms of conjunctions and oppositions. I'd like to show them to you and see if Ptolemy's model can accomplish them. Okay? So I've chosen those very, very key high points, very natural points, things that we can more easily think about, not going into the weeds of positional astronomy, and see if Ptolemy's system can accomplish those kinds of things, that those things will be true in Ptolemy's model. So what is it that we want to be true? Let's again take a step back and review what is the basic motion of the planets through the sky. Like the sun and the moon, the planets move slowly through the starry vault, through the celestial sphere, making various paths through the fixed stars. Like the sun and the moon, this motion is backwards in the sense of from west to east, because the whole sky is moving east to west. That's why we're using that word backward. They seem to move independently of each other, okay, and at varying different speeds. They sometimes are moving faster, they sometimes slow down, and of course, most dramatically, they will stop and reverse and begin to move backwards, and stop again and reverse and start their normal easterly motion, just like the sun and the moon are always moving through the fixed stars in that one direction. They move through the fixed stars, but much slower than the moon. We know the moon is the fastest thing through the, visually through the starry vault. It makes one complete trip in a month. Nothing else approaches that kind of speed. The next speed really after that in terms of the sky would be the sun in a year, and also in a sense Mercury and Venus also pretty much will move through the sky one loop within a year. Mars, Jupiter, and Venus move much more slowly. Mercury and Venus have a maximum elongation. I don't know, that's what the sky watchers have been reporting, guys, and this is what Ptolemy's model is going to have to accomplish. Mercury is never more than about 22 degrees away from the sun in the sky, never. Mercury is always hovering either one side of the sun or the other side. Venus also has a maximum elongation of what we call a bounded elongation. Bigger, about twice the size, about 46 degrees. It can get 46 degrees of angular separation from the sun, but never more than that, never more than that. You'll never see Venus or Mercury, for example, in opposition of 180 degrees. You will never see the sun setting in the sky, and you'll see Mercury or Venus rising in the east, like the full moon. Like you will very easily see that from Mars or Jupiter or Saturn. There's no reason why Mars, Jupiter, and Saturn cannot be in opposition. That as the sun sets in the evening, you will see on the other side of the sky, 180 degrees on the other way, the moon coming up. That would be the full moon of Monday night, or those three planets. Not Mercury and Venus. Why? Nobody knows. This is what the sky watchers have been reporting for thousands of years. And if you want to build a model, you have to make this so. Mars, Jupiter, and Saturn can have any separation from the sun. What is fundamentally different between Mercury and Venus and Mars, Jupiter, and Saturn? Well, Ptolemy is going to build a model that will make those things so. But we'll see, is there a fundamental difference? Has he shown something fundamentally about the way, the cosmos works? Well, you be the judge for that when we take a look at his solution to this. So we have the idea of elongation, bounded elongation for Mercury and Venus, no boundary at all for Mars, Jupiter, and Saturn. That's the other constraint that I want us to think about this morning and see if Ptolemy can accomplish this. One more constraint about this is that when we will connect these elongations to retrograde, because they're connected. The sky watchers have told us in their records for thousands of years that these patterns occur again and again and again for as far back as these records exist. I want us to take a look at that one final, well, before we get to just a couple of visuals to try to understand better this idea of elongation. Here's a nice picture of Mercury in the morning. And right before the sun comes up, you can see as a number of different days, we can see where Mercury is. You go out there at 5 o'clock in the morning every day, a few minutes before the sun comes up, and there's the changing height of Mercury in the sky. And you can see that it's very close to the sun because the sun is right here. So the angular separation of the sun and Mercury is never very big. And the biggest it gets, like I say, is about 22 degrees. It'll rise and rise and rise, and all of a sudden it will stop rising. It'll begin to start to fall again. This is a characteristic of Mercury and Venus. It never gets very far away from the sun. The sun won't let these two planets go. They can bounce back and forth on either side of the sun, but they can never get very far away. Not at all true, not in any way true about Jupiter, Mars, Jupiter, and Saturn. Okay, final review before we plunge into the behavior of the planets and then Ptolemy's geometric explanation for them. The dual motion of the sun about the Earth. Right? Here we look at the Earth down from the North Pole, and we see that the sky, depicted by the constellations of the zodiac, move this way. Okay? They move counterclockwise because we know the stars will rise in the east and set in the west. So here's us on the East Coast. We know that the sky is turning this way every day. However, the sun here in Aquarius moves also through the sky. The sun also moves through the constellations. Basically, why? Well, one of the simplest explanations is that the sun just is simply not moving as fast in this direction. It can't keep up. It falls behind. So after another month, we'll find it has fallen behind, it falls behind, it falls behind. And so we have the annual motion of the sun going, and this is what I mean by the opposite direction from the normal everyday direction of going from east to west. And this is the path through the sun. This is depicting of the zodiac, the constellations of the zodiac along the ecliptic. And this is the overall motion of the sun through the sky, taking 1 year to make one revolution. Okay. I hope this idea here is we're comfortable with from this geocentric point of view. And I'll just mention again, this is a very, very useful model when you study positional astronomy in detail. If you take a course in positional astronomy, you will spend a lot of time in this model, in the model of the geocentric universe. Okay, basically the two-sphere universe of Plato. It is a very, very useful model to think about and understand the relative motions of these bodies, even though we know now, of course, it's completely untrue. It is a useful model to explain and to hold in our mind all these various different constraints and how they work and what their relationships are to each other. All right, we're ready. We're ready to look at the motion, first of all, of Mercury and Venus. They are basically the same. One is just an exaggeration of the other. Everything you can say about the motion of Mercury is exactly the same for Venus, except the elongation for Mercury is only about 22 degrees. The rubber band that the sun holds on Mercury as it bounces back and forth is a much tighter one, whereas it gives Venus a much wider range of about 48 degrees. But the same cycle I'm going to show you goes through the sky. The sky watchers have been reporting for thousands of years. The bounded elongation of Mercury and Venus. So here we have the path of the planet. It makes no difference which one it is, because it's basically the same. This is what we mean by a conjunction, right? From the Earth, we look here at the sun and we find that the planet, Venus, let's say, is in the same place in the sky. This is like the new moon. This would be an elongation of 0. Well, the cycle begins here, okay, at a certain distance away. This distance, like I say, for Venus gets to be no bigger than about 46 degrees. You will never see Venus here, or God forbid, here in opposition. Never. Okay. Just as you will never see any of the planets near the North Star, because the North Star is not on the ecliptic, you will never see Mercury and Venus in opposition. You will never see them rising like the new moon, or rising like the full moon, just as the sun is setting. Venus is also always very close to the sun. So we know that Venus will move through the sky, okay, in its easterly direction. This is the way the sun is moving. The sun is moving east. Venus is moving east. Mercury is moving east. Everybody is happy until we get to a certain point where that motion stops. For some reason, the sun will not allow Venus to get any further away from it than that point. It reaches its maximum eastern elongation. It slows down and stops. The sun does not slow down. So what happens is Venus will fall back. As it begins to move backwards, going in the other direction, it will pass the sun by, going the other way, having yet another conjunction, and continue on the cycle, going on forever and ever, going back to that maximum western elongation and swinging back and forth and back and forth. And this has been going on for as long as we have recorded records. What's important to realize is this is the definition of retrograde. This is the motion opposite of the regular motion. This is the motion opposite the motion of the sun. This is the retrograde motion, and this is where we must have the planet at its brightest. It must be closest to the sun here. Okay. By my picture, it doesn't look like there's any difference. It swings this way, it swings that way, and it looks very much like these are all concentric circles, and I'm not showing any change in distance. Therefore, I'm not showing any change in brightness. This is what Eudoxus was able to do. He was able to build a geometric model to depict this kind of cycle without any change in distance. Ptolemy is going to do better. Ptolemy is going to elongate this, expand this into a three-dimensional picture, or at least a two-dimensional picture, where there will be a change in distance. And so when we get to the retrograde motion, we better be closer to the Earth than in its normal motion when it's going with the sun, catching up to the sun, passing the sun, etc. So that's what I want you to hold. Let's take a look at that picture, that video that we saw a while back. We can get through these obnoxious videos, these commercials. Take a look at what it looks like in the sky. Pictures are one thing, what they actually look like in the sky is something else. Okay. So here's the motion of the sun. Here's Mercury and Venus very close to the sun. Mars also seems to be close to the sun right now. Saturn seems to be close to the sun right now. Everything looks pretty like everyone, everyone is everybody. Everyone can do anything. But there's that loop of Mercury. Okay? Mercury was getting just so far, and the sun pulled it back, and it went into its retrograde motion. That thing that's zooming by the way, is the moon. What's it's going to do this once every month. It just zooms by every month. And I'm going to watch the clock to show you the beginning of this cycle. I know where I wanted to start. We're just watching good old Father Time. We're looking at the slowest of the planet, Saturn, going back, rocking back and forth, moving to the east, retrograde to the west, moving a bit further to the east, retrograde to the west. We're watching this. There's the retrograde motion of Saturn. There's the moon racing through the sky once every 30 days or so. And I'm watching right here. Okay. What I'm going to do now, guys, I'm going to slow this thing down so we can watch the motion of Mercury more normally. So let's cut the speed in half. And let's play this thing. Yeah, I mean, Mercury is the winged god, right? Mercury is the messenger of the god. Mercury is the fastest of all the planets through the starry vault. That's why we're going to slow this thing down. We should see Mercury up in that corner there, up here. I'm sorry, I'm in the way, but I apologize. There we go. Here's Mercury coming down. The sun can't be far behind. Okay, the sun cannot be far behind Mercury. Mercury right now is in front of the sun. It's moving east, moving perfectly normally. And there's the sun. And this is about as far apart as Mercury is ever going to get from the sun. Okay, it's about 20 degrees. These are 10-degree markers. From here to here is about 22 degrees or so, straight line angular distance. This is as far apart. Mercury will now stop and begin to move backwards. This is its retrograde motion. The sun continues to move always in the same direction. And that separation between Mercury and the sun will close up. There's the retrograde motion of Mercury, closing up a new conjunction where Mercury and the sun are in the same place in the sky. Mercury continues to move in retrograde. It'll move to a certain maximum, and that's all. That's as far back as Mercury will ever go. And then it begins to move normally again, chasing the sun, being able to catch up to the sun because it is the winged god, it is the fastest of all the planets. And yes, it'll catch up to the sun, pass it by, and the whole cycle will begin again, over and over and over again. It takes about, I want to say, about 200 days for this cycle to take place. So that is what we mean by the elongation, the bounded elongation of Mercury. So what we're going to try to track, guys, for Mercury and Venus is bounded elongation. Can Ptolemy accomplish bounded elongation? We're going to get our dimmest part of Mercury and Venus, that is its furthest point away from the Earth, during the easterly conjunction, when it's moving in its normal way, just the way the sun moves. And we're going to get its brightest point. It should be closest to us when it's in the westerly conjunction, which of course is the retrograde. That's what we're going to try to see if Ptolemy can accomplish this constraint. If he can't, he doesn't have much of a model to explain what the planets do in the sky. All right, let me stop here because the motions of Mars, Jupiter, and Saturn are a bit easier. Anyone a question or a comment about that bounded elongation, that swinging back and forth on either side of the sun by Venus and Mercury? A question? I appreciate positional astronomy is not an easy subject. It takes a long time to get your head into it, and we haven't had a chance to spend that much time doing it. That's why I'm only picking a very, very, very limited number of ideas that we can hopefully keep some kind of track of. All right. Last piece. We want to look at some constraints of Mars, Jupiter, and Saturn. They are all the same. They have the same constraints. Mars is the most, again, exaggerated. Jupiter is less so, and Saturn even less so. You notice the retrograde motion of Saturn there, chugging back and forth, very, very small, very little chug back and forth compared to that compared to the retrograde motion of Venus and Mercury that we saw. Well, Mars has by far the greatest retrograde motion. It makes the greatest loops back and forth in the sky. Jupiter and Saturn basically have the same loops, they're just smaller. Why? I don't know. That's just what the sky watchers show. Ptolemy is going to have to make this true. Why? Fundamentally, well, Ptolemy doesn't know, but he's going to build a geometric model to make it so. Okay. So here we have the Earth in the center, and here's our sun, and here's our planet. Think of it as Mars. This is what we mean by conjunction, okay? That is, Mars and the sun are in the same place in the sky. They're behind the same constellation in the zodiac. Okay? Here's opposition, where the Earth is in the middle, Mars is on one side, and the sun is on the other. This is like the full moon. This is like the new moon. Okay? Notice there's no problem with Mars, Jupiter, Saturn having any elongation they want, from 0 to 20 degrees to 46 degrees to 90 degrees to 180 degrees. We can find Mars, Jupiter, Saturn anywhere with respect to the sun. However, there is going to be a constraint. Okay? Final constraint, final one I want you to try to hold in your thought. We start with conjunction. We have the Earth, the Sun, and Mars here at position 1. The sun, of course, is always moving in this direction, always going counterclockwise, never changing, no retrograde motions for the sun. And here is Mars going around in the same way, going counterclockwise, moving with the sun. It'll move for a while until Mars gets to here. Mars is going slower than the sun. By the time Mars gets to position 2, the sun will get to position 2 here. It moves much quicker around the Earth than Mars does. The sun takes about a year to go around. Mars takes about 2 years. Jupiter takes about 12 years. Saturn takes about 30 years. So by the time we get to position 2 of Mars, the sun has moved all the way around to here to opposition. Mars is now in opposition. Here's the Earth in the middle, Mars on one side, sun on the other. Definition of opposition. This is where we need to have retrograde motion. This is where we need to have the brightest. This is where Ptolemy's model better show that Mars is at its closest and in retrograde, because we know retrograde goes with brightness. We have to have Mars, when it's in retrograde, be closest to the Earth and in opposition to the sun. He's got to get that right. How does he build his geometry to make this so? Okay, these are the constraints that I want us to look at. There are a million others. Okay, the mathematics here of Ptolemy's system, you can imagine, is overwhelming. Okay, I've picked out these because we can think about them kind of visually and also show them visually in this, they're very simplified geometric Ptolemy that I'm going to show you. Question here, because we're basically done now. We're basically going to begin to look at Ptolemy's model, seeing if he can get these 3 or 4 facts right. The 2 or 3 facts about Mercury, Venus, the 2 or 3 facts about Mars being representative of the other 2. Can anyone ask a question? Anyone will make a comment before we go on?
Peter, are the different orbits here all concentric? It looks, for example, like the sun's orbit is offset a little bit.
Yeah, Mike, don't take that too seriously. Yes, we do know that Ptolemy did use the eccentric point, and that those orbits of the planets are not on center. These are very, very simplified. These are not Ptolemy's pictures. These are the sky watchers' pictures, depicting what the sky would look like during these different configurations. So these really are not orbits in that sense. We'll come to Ptolemy's orbits in a few moments. I'm just trying to depict what the sky would look like as you sit in your lawn chair with the sky watchers of 100 years ago, or 1,000 years ago, or 4,000 years ago, and how you guys can agree on a very simple picture like this of what must be going on above us. We'll come to Ptolemy's pictures in a moment to make these pictures true. Okay, so again, in opposition, this is when we need to go into retrograde. Brightness, retrograde, and in opposition. Those are the 3 words that we need to keep so for Mars. So no bounded elongation, brightest at retrograde, in opposition, dimmest in that easterly conjunction right here. We should be furthest away from the Earth here. We should be closest here. Notice that we're the same. Okay, this is not a picture depicting any of that. It's simply trying to capture business about the opposition and conjunction part of it. How to put all of this together, Ptolemy will do this, and I'll show you in a moment. Okay, so a few thoughts about Ptolemy before we go back to our pictures, the Ptolemy's model. Ptolemy, you can see his dates are in AD, who worked his whole life in Alexandria. Certainly, he's the most influential astronomer of the ancient world. Hipparchus is the most creative and the most important in terms of the contributions to astronomy and how to build astronomy. And Ptolemy will tell you that he's using the ideas of Hipparchus to do this. He did many other works. He was also a great map maker. Quite impressive, the map that you're looking at here of 180 AD of the European continent. Very, very impressive. Again, we're talking about the Roman world here. We're talking about the military world of Rome, their roads and their map-making ability. But this is a map made by Ptolemy for them out of Alexandria, piecing together all the information from the empire to build a map like this. This is the greatest peak of map making in the world until we get to the world of the Renaissance. It peaks here also in Ptolemy. Okay, but we move on to his astronomy. His great book is called, his original title was The Mathematical Compulations. Can't get more boring than that. The Islamic scholars called it the greatest of something or other, and the Latin West just simply, shortened that to the Arabic word, or the Latinized Arabic word for the greatest, the Almagest, and that is the title of Ptolemy's work that has come down to us. It is called the Almagest, some kind of a corruption of the word greatest of Arabic, because that was the elongated, longer title that the Arabic astronomers gave to this work. And you can see the difference. You can see the epicycles. You can see these are all pictures. By the way, these are from the Islamic translations. If you look closely, these are all in Arabic. This is not the Greek original. These are the Arabic translations of the Almagest. It basically uses a completely Euclidean style. Starts with hypotheses and axioms and proves theorems, definitions. Very much looks like Euclid's work. Euclid is the model of all mathematics, well behind Ptolemy. Newton's Principia looks like Euclid's elements. And it very much follows the cosmology and the physics, natural motion of Aristotle. We won't worry about this too much of this today. This will become much more relevant to us when we want to overturn this model, when we come to Copernicus, and we see why people don't like Copernicus, because Ptolemy is following Aristotle's ideas and Copernicus is not. We won't worry about that until we get to the controversy of the scientific revolution. We want to focus today mostly on the geometry. Ptolemy has one more trick to put in the bag of all the different devices, and this is called the equipoint. Here we have the Earth. Here we have the Earth off center. Here's the deferent circle, which is the center here is not the center of the universe. Here's the center of the universe, but the path of the deferent circle doesn't have its center, the center of the Earth. That's okay. This is the eccentric point, the off center. He gets this from Hipparchus. And here's our epicycle going around the deferent circle, and here's the planet going around the epicycle. Okay, this is basically the Apollonius mechanism. What Ptolemy wants to do, he wants to introduce a new idea of the equipoint, it's called. He simply takes a point exactly symmetrically on the other side of the center of the deferent. Wherever the eccentric point of the Earth is, the equipoint is not some arbitrary place. It's exactly on the other side from the center of the deferent, equidistant, just as the distance from the center to the Earth. We have the distance from the center now to the equipoint. This defines where the equipoint is. What's the big deal with the equipoint? The big deal with the equipoint is that what Ptolemy wants is he wants the motion of this point to move truly at different speeds. Yeah, this is a real no-no. He actually wants this point not to be moving at a constant speed around the different. He wants it moving slower around here when it's far away from the deck. I'm sorry, he wants this moving closer, faster. Start again. He wants this point moving faster when it's closest to the Earth, truly faster, not looking like it's faster the way Hipparchus did for the sun. He wants it to moving truly faster here. And when this point is over here, as it's carrying around the epicycle, when it's far from the Earth, he wants it to be moving slower, truly slower on its path. Why does he want this? Because he can build a better model. He can save the appearances better. His tables are more accurate if you give him this additional degree of freedom. He wants the speed of the epicycle to truly vary as it goes around the different circle. Okay? That's what he wants. And the way he gets it is that he thinks of this point moving not with respect to this Earth, but with respect to the equipoint. I'll show you with animation in a minute. That he wants this point to be sweeping out with respect to the equipoint. And if he does it that in the right way, he will get the planet to be moving faster. I'm sorry, get this point to be moving faster here and slower here. This is a large step away from the cosmology of Plato and Aristotle. Most of the Islamic astronomers rejected this and found they did not use this mechanism. I'll show you how powerful it is in a minute. Copernicus completely rejected this. Many historians of science say one of the main reasons why Copernicus went to search for his new model was because even with his equipoint, which clearly is illegal, Ptolemy's system wasn't all that accurate. It was just getting more and more complicated. It was getting further and further away from the true principles of cosmology as laid down by Plato and Aristotle. There had to be a better way, because this was the last straw for Copernicus, that we had to come to use this equipoint mechanism to truly move things at truly different speeds. How does the ether, how does the beautiful, perfect world of forms move at varying speeds? How is that possible? It's not. It's not. The only possible motion is in circles, combinations of circles, at constant speeds. What else could it possibly be? What could possibly slow these points down? What could possibly make these points go faster? You can't imagine it. You can't imagine what that answer would be in their mental furniture. This was simply not allowed. What's Ptolemy doing here? He says, I'm a mathematician. I'm not a philosopher. I'm not a theologian. Plato wants me to save the appearances. This is what I need to save the appearances. You let me make this point move at a varying speed, and I'll build you tables which are more accurate as to where things are in the sky, in the past, in the present, in the future. Full stop. What do you want? You want your theoretical cosmology, or do you want your appearances saved? I can't give you both. Well, Ptolemy built a beautiful model using this very powerful device. We will not use this device for us in anger here. This is a very complicated device, as I'll show you in a moment, and it won't involve our constraints that we're looking at. But this is very, very important historically. This is something that most of the Islamic astronomers rejected and Copernicus rejected. And interestingly, the Islamic astronomers went ahead and found a different device. They went ahead and made an epicycle on top of an epicycle. They put another epicycle here, a small epicycle, and put the planet on top of that. They found that that could do, in many, many ways, the same kind of job of what this equipoint can do. Copernicus, of course, kind of threw the book out in terms of the geocentric system. What's interesting about the Islamic astronomers, as much as they completely understood the Ptolemaic model, completely mastered it, extended it, modified it, enhanced it, they never broke away from the basic paradigm. Okay? The most creative that they got, the most radical that they got, for all their great mathematics, was to add on something like an extra epicycle, which makes things incredibly complicated. You can do all kinds of tricks with a second epicycle. Okay? But they never fundamentally broke away from the Ptolemaic paradigm. Copernicus does that. So let me show you. First of all, let me remind you what we're talking about here. We are not talking about circles. We are talking about three-dimensional spheres. This did not change. Copernicus was dealing with three-dimensional spheres. The first person who gets rid of these spheres, we'll see in the scientific revolution, is not Copernicus. It is astronomers who come after Copernicus. This explains very nicely, guys, the business about everybody being along the ecliptic, right? Because basically, here's the Earth, here's the planet here, here's the center of the different, center of the epicycle, going around the different sphere. All you have to do, right, is to get the planet to just a little bit above the table and a little bit below the table, because this plane here, this is the ecliptic. This is the plane of the ecliptic. Okay? So how do you get this red dot, this planet, to be sometimes dipping a little bit below, sometimes it dips a little bit above, but it doesn't go too far? All you have to do is just change the axes of these spheres a little bit. Let it tilt a little bit. So as it's turning around, as it turns around, it goes up a little bit, and then it will go down. It'll send it very, very gently up and down. It'll be above the table and below the table. If that's not enough, you can go ahead and turn the epicycle sphere. Give it a little bit of a twist. And so as this thing goes around, sometimes it rises above, sometimes it rises below, and you can play all kinds of wonderful games here when you're working in 3 dimensions. And this is the way, from the perspective of the Earth, as we see the flat 2-dimensional picture of the celestial sphere, we can see where sometimes it drifts above the ecliptic and sometimes it drifts below, but never too far away for all the planets. This is very nicely accomplished by the Greek idea of the planets being carried around by these spheres. All right. The equipoint, the infamous equipoint. We start with the eccentric point. Okay. This is okay. As long as this point here will move at a constant circle, we're in the world of Hipparchus. We're in the world of modeling the sun very, very accurately. But this is not what Ptolemy is up to. This is what Ptolemy wants. Whoa, slow down, speed up faster than resonance. It's like an amusement park ride. This is definitely a change in speed. That different point, that center of the epicycle, or the planet itself, you can make a planet do this. You can have the sun do this. This could be a more accurate model of actually the sun's motion. Let the sun truly move along the ecliptic at varying speeds. Okay. Or if you want, you can put an epicycle on here and have the epicycle being turned around at changing speeds, and simply put your planet on top of the epicycle. Okay? This is what Ptolemy wants. The purists of the world say, no, you can't have this. Nothing in the sky could possibly move like this. I don't care what geometry you show me, you can't get this to be so. You can't use this mechanism. This is too radical. Thomas says, but it's really not. Look, all that I'm doing is I'm just taking this point here that I call the equipoint, and look at my red dot. My red dot is going around the equipoint at a nice constant speed. Come on. The red dot, this purely geometric point, is moving around the equipoint at a nice constant speed. And what do I have the planet doing? I have the point of the planet, or the point of the different epicycle circle, or the planet. I just simply have the blue dot being controlled by the red dot. Okay? I simply have the blue dot as a projection of the red dot out on the original path. So if you can agree with me that the red dot is moving around the equipoint at a constant angular speed, never mind its regular speed is constant, but its angular speed is also constant, then the blue dot is also moving around the equipoint at a constant angular speed. I got something constant going here. Yes, because of the projection, sometimes close, sometimes far away, I'm getting a difference in speed, but this point, this blue point is moving around the equipoint at a constant angular speed. Come on, give me a break. I'm not going that radical. It's just not that radical. No, I think it's too radical. I don't like this. You can see, though, how powerful this idea is. Okay, because once you start allowing a mechanism like this to be used in your model, there's no reason why you can't put your planet here with the epicycle, going around the epicycle. You could go ahead and cook it up so that the planet could also go around the epicycle at actually different varying speeds. This is too much. This made the Islamic astronomers and Copernicus' head explode. What are you doing? You can't. There's something fundamentally wrong with what you're doing here, Ptolemy. This system is beginning to break down. Now, of course, this is in Ptolemy's original system. This was not breaking down. This was one of the great innovations in the history of the world to build such a system like this. But as the centuries went on, and as more and more astronomers looked at this system and tried to improve it, tried to make the tables more accurate, because they would always drift off. The accuracy would always drift off as you went further and further in the past or further and further in the future. Try to bring it back to try to make it more accurate. They always came back to this mechanism and say, this incredibly powerful, illegal mechanism, even this doesn't help us create the accurate tables far into the future. And so therefore, there's something wrong here. This is so complex. This is so rich. This is so flexible. And I still can't get it right. What the heck is going on? Well, the Islamic astronomers went ahead to their dual epicycle, among other things. Okay? And I don't want to simplify it to just one thing, but this was a very great innovation, and that's called the Tutsi couple. And they're able to play all kinds of wonderful tricks and make wonderful perturbations of the paths using this Tutsi couple. Copernicus said, no, I just can't go here anymore. I'm going to sit down. I'm going to rethink this. What else can we do? Can we go back? First of all, we need to go back to first principles. We need to go back to fundamentals, circular motion at constant speeds. All right. Can't change that. I have no option of changing that. Okay. This is the cosmology of Plato and Aristotle. This is now the doctrine of the church. I have no option here. I must stay within Plato and Aristotle's cosmology. What else can I do? And what historians of astronomy, science have said is what he did was he went to the geocentric model and began to look at it. He went back to the records. He went back to Aristarchus. He went back to the Pythagoreans. He went back to all those writings and said, who else did this? Anybody do this? And he found that there were precedents for this. And he began to develop his model because this mechanism broke the back. All right. So let us take a look at Venus and Mercury and see if he gets it right. Here's the beautiful path of Venus going around the Earth. It's very simple. We have our purple difference circle. We have our epicycle circle and our planet Venus or Mercury going around the epicycle as the different point goes around the different circle. And there it's close to the Earth. There it swings far away. And here it comes in close to the Earth again. Right here, there's Venus close to the Earth and swings far away. We certainly have a difference in distance and therefore a difference in brightness. Can he get bounded elongation and retrograde motion when we're at its closest? That's our question. And here's Ptolemy's answer. Let's get our orientation. Here is the Earth. Here is the sun, and here is our planet. Yeah, he's going to put the sun into the picture because the sun clearly has some kind of constraint on Venus. Venus is bound to the sun in some way. Let's take a look just at the motion the sky watchers see. Here's Venus running ahead of the sun, normal direction, the same way the sun moves towards the east. Here it will slow down, come back, cross the other conjunction, moving in retrograde, going further and further back until at some point it goes no further back, and then it begins to chase and catch the sun again. This is what the sky watchers report. Here we have the change. Here's the brightness. Better be retrograde there because that's where it's bright. And here, when it's far away, that would be the normal conjunction here. So let's take a look at the line of sight. There's our normal conjunction. And watch now when it gets close, watch the little, there it is, right there. There's the tiny little retrograde. Watch it again, guys. Venus will, there's the retrograde right there. Notice also that the blue line and the black line are never very far apart. They get as big as, for Venus, about 48 degrees, for Mercury, about 22 degrees. They never get, the planet never gets, its elongation never gets any more than the bounded elongation allows. How does Ptolemy do this? By a simple Apollonius mechanism, no big deal, of deferent and epicycle. Well, let's catch our breath and take a look. What he does is he takes as his deferent circle a circle concentric with the path of the sun. Now, here's the deferent point on the deferent, and this is what controls the epicycle. He will make sure that this point is always in line with the sun. This is why the planet gets dragged around with the sun. This is why Venus can never be very far away from the sun. How far can Venus ever get? It's only on a circle like this, and the circle is always keeping up with the sun. So how far can Venus be from the sun in the sky? That far. That's as far as Venus can ever get from the sun in the sky. Our measurement, here's the sun and here's Venus. This is as far away as it'll ever get. What is that? It is when our line of sight is just tangent to the epicycle circle. Isn't that pretty? Yeah, the tangents appear again, okay? Because anything more than that, it'll start to move into this epicycle circle and it'll start to get closer. There, it's cutting into it. And so therefore it's getting closer to the sun. Closer and closer. Okay, Venus will catch up to it, pass it by in that conjunction. And as it gets brighter and brighter and brighter, as it moves into retrograde, just at the other conjunction. Ptolemy has it right. He has retrograde and brightness and bounded elongation. A beautiful geometric solution. It's right there in front of you. The three constraints that I picked for us to think about is right here in this picture. Bounded elongation, because the deferent circle is bound to the circle of the sun. Bounded elongation, because the epicycle circle is picked to be a size so that its tangent line will only be as big as what the bounded elongation is, 22 degrees for Mercury, 48 degrees for Mars. Retrograde is coming up right here. Retrograde is at the closest. Right there is the little retrograde loop. Done. The model of Venus and Mercury are 1,000 times more complicated than this. I'm just trying to show you a central feature of how Ptolemy's geometry can do this. Of course, what Ptolemy will do now is build tables of the positions of Mars. Anytime in the future, anytime in the past, you can check his past with his past records to see how accurate his model is. And of course, it makes predictions in the future for the astronomers and and most particularly the astrologers. The astrologers want the predictions in the future so they can tell their kings and pharaohs and everybody else all the good news and bad news that's coming their way by the influence of the planets on people's lives. Questions about this solution? Anybody make a question, a comment? The beautiful solution. Notice that this is why Venus and Mercury have bounded elongation. According to Ptolemy, all you need to do is just make sure the deference circle is determined by the sun. If the deference circle goes around just the way the sun goes around, then the epicycle will have to be always directly in front of the sun. So when I'm looking at the planet, I'm always looking towards the sun. The planet is never very far away from the sun in the sky, bounded elongation. And we know that the retrograde is made very nicely by when it gets close like that little loop, that wonderful Apollonius loop of the inside gives us the retrograde. Okay, so we have solved the constraints that we were looking at least, for the motion of Venus and Mercury. And it explains why Venus and Mercury are special in Ptolemy's system, of why they have bounded elongation and the other three do not, because the fact that this deferent point is always in line with the sun and the epicycle is always keeping up with the sun, sometimes on one side, sometimes on the other. And now for Mars. Does he get Mars right? Okay, we know from Mars, we've looked at Mars before. Nice big epicycle, okay, that you need. Sun, the Earth is in the middle, no sun yet. And so there's the motion Mars far away. Yeah, Mars gets close, gets bright, better be in retrograde. Far away, better be in opposite, better be in conjunction. Close, better be in opposition. These are our constraints. Conjunction with the sun, same place as the sun. Retrograde, close, better be in opposition, the opposite side from the sun. All right, let's look at the retrograde. We've looked at this before. I'm sorry, let's look at the path. There's the actual path of Mars around the Earth. And we will get our nice retrograde loop right there in here. Right there is where we'll get the retrograde. Let's look at it. Here's our line of sight. And there's the big retrograde, big backward motion through the stars as it moves along normal. Okay, so far so good. We've seen this before. Now we have to add the sun. What is it that we're adding? Mars must coordinate its motion with the sun. Right there, the sun better be in, we better be in opposition. And right here, we better be in conjunction. The sun better be here, somewhere between, be in the same place in the sky as Mars. And during retrograde, when it's closest, right here, the sun better be over here. Mars on one side, sun on the other. That's what the sky watchers have been reporting for thousands of years. I need the sun to be in opposition during right retrograde. Otherwise, my model is no good. Let's see his solution. Let's get our orientation. Here's the Earth in the center. Here's Mars out here on its in its path. Here's the deference circle, and here is the sun. I've introduced the motion of the sun going around the Earth, a smaller path than the path of Mars. Mars is outside of the path of the sun in Ptolemy's system. Jupiter is further out and Saturn is further out. We'll see the overall picture in a minute to finish up the class. Just trying to get the motion of Mars correct here in his model. Okay, so we'll let Mars move. There's the retrograde that we know so well. There's the conjunction, right? When Mars is far away and it's dim, it's on the same side of the sky as the sun, like the new moon. However, As we come into retrograde, as we get brighter and brighter and brighter and brighter, at its brightest, Mars is in opposition. The sun is on one side, Mars is on the other. Mars is rising at 6 o'clock in the evening, just as the sun is setting. Mars is directly above our head. Mars is on the meridian at midnight, because we know the sun is directly underneath our feet at the other side. This is what the sky watchers have been reporting for thousands of years. When Mars is at its brightest, at its closest, going into its retrograde motion, it must be directly above us on the meridian at midnight. That's what it means from your lawn chair. I know this is not easy to make these connections so easily. We should spend a month doing planetary astronomy to be more comfortable with this. So I appreciate this is not all that easy to absorb in our heads so easily. I do very much appreciate this. But this is the constraint that we want. And this picture does in fact show it. But how does Ptolemy go? There's that conjunction. There's the opposition. Is Ptolemy just cheating? Is he just making Mars and Sun go around in these rates just arbitrarily so that these things happen? He could do that, okay? Because each planet is actually laid out individually, but he has a scheme. He has something that he's going to make why this constraint is show is because he's going to introduce a geometric constraint, and this is the last one I really have for you. And that's this parallelogram. This parallelogram that I took away. Let me get it to come around here for a minute. What Ptolemy insists upon being so in the sky is that he's going to determine how quickly Mars goes around the epicycle. Mars will go around the epicycle at a certain rate so that the direction from the center of the deferent to Mars is always parallel to the direction that we see the sun. The direction that we see the sun in the sky, this parallel direction here of sight will always make that this line here also parallel. And since the sun is going around the sky, around the earth at a certain rate, it'll determine how fast, if you want to make this so, if you want to make this a parallelogram, if you want to make these two lines always parallel, it'll determine how fast the red Mars has to go around the epicycle if you want this line always parallel to this line. This line we know. We see the sun in the sky. We see the sun going around the ecliptic once a year. He's going to determine the position of the sun, of Mars in its epicycle to always have a parallel direction geometrically that the sun has to the earth. And with that, he gets this. I've made the sizes actually equal. In Ptolemy's model, you don't have to have them equal. It was just easier for me to program it this way. But here is this changing and collapsing parallelogram. It's determining the motion of Mars around its epicycle. And here, when it collapses here, this is the collapse of opposition. The sun is on one side and Mars is on the other. And here, the collapse going the other way in conjunction. When it collapses once more, here, it's the sun and Mars are on the same place. But clearly, so we now have a way to determine the speed of Mars going around its epicycle determined by the sun. And this will create the constraint that we need of no bounded elongation. You can be anywhere you like in the sky with respect to the sun, Mars. But when you go into opposition, you better be in retrograde. When you go in opposition, you better be closest, brightest, and in retrograde. And that's exactly what we have right here. We have closest, in retrograde, in opposition to the sun. Okay? So that's it, guys. That's basically the model. We'll finish up with the last couple of slides, but this is a beautiful system. I've simplified it to the point where we can absorb in one class just some of the fundamental ideas of what Ptolemy is trying to work with here and trying to get right through his beautiful geometry. A question before we just finish up with the last few slides of the overall pictures. A comment. I know this is a lot to keep in your head at one time. Opposition and retrograde and brightness, and I know it's a lot. It's a lot. Okay, so here is a basic the system of Ptolemy, a very simple the depiction of it. It's important to realize that each planet was laid out by Ptolemy individually. This is not a system the way Copernicus' system is going to be. Okay, he took Mercury and he took Venus and he laid out how big the difference had to be in the epicycles, and he went ahead and figured out Venus, and then he put that aside and went ahead and then did Mars, and he did them all individually. The reason why you can get away with that is because there's no depth perception in astronomy. You can't tell how far things are away. It doesn't matter how big these epicycles are in terms of the depth perception. It's just going to show different brightnesses is what it's going to show up on. So it's a very accurate model, but and here's how he shows summary of how he gets that bounded elongation. Okay, by keeping the sun always in front of the centers of the epicycles of Venus and Mercury. Venus and Mercury can never go too far away. Really running out of time. One last idea before we close up is that notice that the epicycle of Venus bounces up against the epicycle of Mercury. And the epicycle of Venus kind of goes up against the sun. And the epicycle of Mars kind of touches the epicycle of Jupiter. They're all kind of like a nested onion. They all almost touch each other. This is not a coincidence. This is something part of Aristotle's cosmology that he insists that there's no vacuum. We'll look upon this, and we'll look at this in the spring. But Ptolemy also gets this right by choosing the sizes of the difference in the epicycles to have everybody squeezed up against each other. The distances that he finally uses, he doesn't make much about distances, but the distance that he does get is a more accurate distance to the moon. Instead of being 34 Earth diameter, he gets actually down to 30 or 60 Earth diameter. But for the distance to the sun, which is so fascinating to me, he uses his Aristarchus' distance. In 350 years, no one had been able to improve upon Aristarchus' model of how to find the distance of the sun with those bad measurements. Ptolemy uses Aristarchus' distance for the distance of the sun. Okay? So the strengths of the model, you can read. The weaknesses of the model, again, big one about this varying size of the moon being too big and too large in the sky. This will plague everybody. Copernicus actually will finally make some progress on this. This also plagued the Islamic astronomers to try to get the motion of the moon right with its distance be under control. Very difficult to do using the epicycle different model. And the equipoint. Oh, big weakness as far as the other astronomers were concerned as time went on. Okay, we're really out of time. This was the last thing which you math types can do yourself. We're looking for another skinny angle approximation. We're setting up this geometry of the parallax of looking at the moon, and we're looking at this skinny triangle here. And we're going to get a skinny triangle. We're going to get this angle measured, and we're going to get a nice skinny triangle approximation where the angle is to 360, as this distance between the two cities is to 2 pi d, and the distance to the moon. And he actually gets 31 Earth diameters. 38 for Aristarchus, 34 Hipparchus. Ptolemy gets it down to 31. Okay, guys. Thank you for your indulgence of that extra 4 minutes. Any questions before we wrap up? Are you all totally zonked with information to try to keep up? I appreciate it. That would be the case.
Peter,
Yes.
so how did he put all this together? Did he do it in stages, or was it a eureka? I mean, in
We
his
really
study?
don't know. It's a good question. We really don't know. We just have his work. We don't have, drafts of his work. It's so long ago. We just have the work originally in Greek and then translated into the Arabic and translated from the Arabic into the Latin. And finally, the Greek was originated. All we have is that original document, and there it is. It's this monument of mathematics, and it just stands as one of the great intellectual achievements of the human race, Ptolemy's system. From that system of geometry, you can build these tables, and the tables will show you where the things in the sky will be. And that was the game, was to build these tables.
So he didn't in any way publish as he went along.
No, we have no record of his work like that.
Mhm.
Yeah.
Thank you.
Remember, we're talking about 100 AD. Any other questions, guys? Comments? All right. Well, I sent you a little write-up for what I'm about in the spring. What I'm going to do in the spring. I do hope that you can join me. Some of you can join me too, because this is where the plot really thickens, guys. When we get to the scientific revolution, and we're well positioned here to look at the scientific revolution. We can see what it's revolting against. You can't have a revolution until you want to revolt against something, and this is what the revolution the revolution is about. This Ptolemaic system and all these cosmology ideas of Aristotle, and how this is torn down by the great figures of the scientific revolution, particularly Galileo and Kepler, and of course, ultimately going to Newton. It's a wonderful story. It's got beautiful mathematics in it, and it'll expand our view of the cosmos and the nature of the universe irrevocably. And it's a wonderful story. I hope you can join me. All right, guys, have a good winter, good holiday, and hope to see you in the spring.
Thank you, Peter, very much. And I'll see you in the spring.
Okay, great.